All right, so we have our 5 different types of decay processes: alpha, beta, gamma emission, positron emission, and electron capture. And so what we really want to focus in on then is the fact that they all have unique changes to mass and charge. So mass referring to how big the nucleus is, and charge is really going to refer to the ratio of protons to neutrons. Are you putting in additional protons, or are you putting in changing a proton into a neutron or a neutron into a proton, and how does that affect the relative stability of the nucleus? And all of these types are going to have characteristic changes. I mean, we can see they all kind of do their own thing. Then their similarities, that positron emission and electron capture, do accomplish the same thing in terms of the net change to the nucleus. So as a result, each type of instability, nuclei with too few protons, nuclei with too few neutrons, or too many of the other, or nuclei that are too heavy. Those are the 3 main ways that we characterize the instability of why nuclei were unstable. Were they too big? Did they have too many neutrons, too many protons? And there is going to be an associated decay pathway that goes along with that. So for nuclei that have too few protons, in order to become more stable, they need to get more protons. So they undergo beta emission. In beta emission, you eject negative charge from the nucleus, right? That is an electron coming out. So if you have too few protons or too many neutrons, that means there's not enough positive charge. If the nucleus loses some negative charge, that's losing an electron, then what's going to end up happening is they'd get to become more stable, right? They'd have more positive charge in the nucleus because they've lost negative charge, meaning they're closer to stability. If there's too few neutrons or too many protons, you either undergo positron emission, where that nucleus loses negative charge, right? If there's too many protons, you lose some negative charge, or electron capture, where you're absorbing negative charge, right? But they're both dealing with the same issue of too many protons, which is too much positive in the nucleus. So either you lose that positive as a positron, or you gain some negative from an outside electron. Then the final method final motivation for instability was that a nucleus was too heavy, right? Our cutoff was 83. More than 83 protons, that nucleus is definitely unstable. And alpha emission is the only way that a nucleus will lose mass, right? If you're just interchanging electrons and positrons and that kind of stuff, even gamma rays, there's no mass change. Alpha emission is the only way, and it's going to be the major predicted pathway when a nucleus is unstable because of size. I'll say there's a caveat. When we predict stability based off size, sometimes those nuclei will undergo either beta or positron emission. But for our purpose, we're just going to always say if it's big, it's going to have to undergo alpha emission. So the types of nuclear instability correspond with those expected decay pathways. You can have too many neutrons, too many protons, or the nucleus can be too big, right? There's that really narrow band of stability, that handful or couple hundred stable possible combinations of protons and neutrons. Everything else around it is unstable, and we can understand spatially, or too many protons, too many neutrons, or is it too big? If we take that same graph, the black dots in the middle still represent the stable nuclides. Everything around it is then color-coded based on the type of decay that nuclide undergoes. So you can see that everything above the black lines, for the most part, has this blue, which corresponds to beta emission. All of those have too many neutrons. They are higher up on the curve towards additional neutrons, and that's why we would say that they all have too many neutrons. The reason why they're unstable is too many neutrons, so they're going to undergo beta decay, get rid of some of that negative charge, turn it into protons. Then, for these things below the curve, where we have too many protons, we can see that orange, they tend to decay via positron emission. They decay via positron emission. They have too many protons. They're going to lose those protons, send them all out. Then finally, our alpha emission shows up in these big atoms, right? Where we have high on the high side, they are unstable. That's the only place where we really start to see a lot of alpha emission. You will note this curve isn't the graph. These colors do intermingle to some extent, and that just does happen. You'll also notice the alpha starts to poke in down here where there's problems with too many protons. Alpha emission, you still lose protons. And so you can lose those sorts of things. The other thing is, you are just kind of, there is potential to do these things. What happens is also kinetically related. Everything we're talking about so far is a thermodynamic idea, but there is some, what is the possible kind of barriers and stuff. But we're gonna use broad strokes. The alpha emission is on the heavy side, and then if it's not heavy, either positron or that beta emission, beta plus, beta minus. All right, so what we want to be able to do then is be given a nuclide and predict which decay process it will undergo, because that will actually allow us to predict what it's going to turn into, which is interesting from a chemical perspective, right? If I start with, say, sulfur 34, what's it going to turn into? All right, so if I want to know what the decay process is, the question of knowing which decay process is always going to be based on why is it unstable, right? What drives the instability? The first thing we can always check is that idea, is it too big? Our cutoff is 83, greater than 83 is unstable, less than 83, we'll say, is not on phase bad. And then we have to look at that neutron-proton ratio, which compare your mass to the atomic weight, right? Look it up on the periodic table, is it higher or lower? And from here on out, if we're talking about nuclei that are decaying, if you're asked to predict the decay process, you don't need to worry about those even, odd, anything. This thing is unstable. We're just going to say it's going to fall apart. You're just going to compare the atomic mass that's given, that number in the symbol or in the name of the isotope, to the atomic weight from the periodic table. Let's start with our sulfur 34. So whenever we are given our isotope symbol, we're going to figure out why is this thing unstable. If it's going to decay, why would it decay? Well, the atomic number is 16 here, so it's not too big. I don't have too many protons. When I look at the atomic weight, then, if I look at it on the periodic table, it's just over 32, 32.07. So that implies that the isotope 32 mass is probably the most stable. 34 is higher. Whenever I see that number is higher, that means there's too many neutrons. If I have too many neutrons, I need more positive charge, so that nucleus is gonna undergo beta decay and lose that electron. So for this problem, we were only really looking at what it would do, but we can go ahead and actually figure out then, what does that look like, right? What happens when sulfur 34 undergoes beta decay? Right? Start with sulfur 34. Beta decay means it emits an electron. And then we follow the same process we looked at before, balance the mass, right? In this case, it has to be 34, which is inconsistent with beta emission. We're not changing the mass. This isn't too big. I don't need to make it smaller. I just need to change that proton-neutron ratio. Balance the charge. This is where we're going to start to see some change. That's the whole point, changing that charge. It was 16. I lost a negative charge, which means it is 17. If I can look up, so I know the atomic number is 17, the mass is 34. I can look it up. That means it's going to be chlorine. Okay, so if you have a sulfur 34 atom, that's going to turn into chlorine 34. When it undergoes decay, you can start to predict those things now. So we can start with you have this nuclide, what's it going to turn into? And so, that could potentially affect what sort of molecule is your sulfur in, is your sulfur atom in. If the nucleus changes and becomes chlorine, does the chlorine atom want to be in that molecule? Thorium-231. Always ask, why is it unstable? Well, we're above 83 for my atomic number, 90. Greater than 83. This thing's too big. One of the reasons I was going to check that first off, that means it's alpha decay. We know right away we would predict that thorium-231 is going to undergo alpha decay. Okay, so it's thorium-231 doing alpha decay. So the product is going to be a helium-4 nucleus or an alpha particle, right? That has 2 protons and 2 neutrons for 4 total particles. Balance out my mass, 231. I lost the 4, giving it to 227. For the charge, it had 90, it lost 2, bringing it to 88. So 88, 227. I can then look up what that is. Atomic number 88 is radium. And again, especially these big ones like this, these atoms, these nuclei are all super radioactive, so we don't use them in chemistry, because if you say put thorium in a molecule, the nucleus is going to change, and all of a sudden you have radium in that molecule. It's going to probably not be a stable molecule anymore. So that's why we don't do chemistry with these elements. But it is certainly there. It could be, we will form radium-227 if you have a thorium-231. It may take a long time for thorium to change, but it will certainly change into radium via alpha emission. Finally, scandium-41. So again, sorry about the table. This one's not too big. Z, your 21 is less than 83. So this is definitely not too big, well within that cutoff. The atomic weight of scandium, if you look up, is 44.96 atomic mass units. 41 is lower than this. So we know that our atomic mass is lower than 44.96. 45 is likely the stable scandium isotope. And so 41 is definitely lower than that. That means there's too many protons or not enough neutrons. That's one of the ways we can think about it. There's not enough neutrons. So we would expect there could be positron emission or electron capture. And so in this case, whenever you are given the fact that there are too many protons, you actually can't distinguish between these two processes. You just know that one of them will happen, either positron emission or electron capture, because in both of those cases, you decrease the number of protons and turn them into neutrons. And so the thing is, it doesn't really matter which one we choose, because if you say it emits a positron, say you're doing positron emission, you balance all this out, you get 41. Again, the mass doesn't change, but the charge does decrease by 1 in the nucleus, so you'd get 2041. So you'd make calcium 41. Okay, so if you have scandium 41, it becomes calcium 41. Very nice. If you do electron capture, though, you end up getting a similar idea. That electron capture, if you go through, you balance it out, you end up still getting that calcium 41 is the product nucleus that you create. So when we say, why is it unstable? It can be either of these processes, either beta emission or electron capture. Whether or not an atom undergoes one or the other is based upon kinetic issues, whichever one has a lower barrier, because both of them are possible. And so both are possible, both achieve the same product nucleus. So in terms of which one happens, it's just based on kind of the specifics of that particular nucleus and what it wants to do. But it doesn't really matter which one you choose, because the daughter that you make out of it is going to be the exact same. All right, so now that we can do this, we could start with a nuclide, right? We can say, why is it unstable? What sort of process is it going to undergo? Then predict what comes out of it. The thing is, when you undergo one decay process, the daughter nuclide is not guaranteed to still be stable. You've just changed one thing about it. All of the decay processes we can see are really small. Alpha emission is the biggest, where you lose 4 total particles. But everything else, you're just kind of changing one proton into a neutron, one little thing here and there. So usually when decay happens, the resulting decay on the other side, the daughter nuclide still tends to be unstable, especially when you have, say, something that's really unstable. It's really big, way past 83, or it has like a really bad proton to neutron ratio. So what'll happen is some nucleus undergoes decay, makes a daughter. Then that daughter undergoes its own decay to make a new one, right? So again and again, and this is overall called the decay series. This could be 3, 4, 5 to 10, 12 sequential steps that a nucleus will undergo until it hits something stable, right? And this could take, each one may take years, a couple years, thousands of years. This overall can take hundreds or thousands, millions, billions of years to go through all of these decay steps, just because there's so many of them. So for example, uranium-238 up there. So uranium is at atomic number 92. So we can see that's really unstable, right? 83 is our cutoff. Anything above 83 is guaranteed to be unstable because it's too big. Uranium's at 92. And so the only thing that's offered to it, you can see, is the first decay it does is this alpha emission. You can see it loses to down here, it goes down, atomic number goes down 2, and the mass goes down 4. Okay, the thing is, you can only lose, a nuclei only have the option to lose that alpha particle. It don't have bigger changes necessarily accessible to them. That's the biggest change. It's still at atomic number 90. This is still unstable. Thorium-234, it doesn't decay as we would potentially expect by alpha emission. There's some beta decays that are in there. But then you hit this uranium-234, and then you can see it has to be 1, 2, 3, 4, 5 alpha emissions. So those 5 alpha emissions happen, and it's still not stable, right? It's at lead, so it is at atomic number 82 now. So it's no longer going to be necessarily unstable because it's too big, but it's still unstable. It has too many neutrons, right? It's got too many neutrons, not enough protons in it. So then what it does is it undergoes some beta emission. You turn some of those neutrons into protons. Eventually it hits to polonium, which is above 84. So it does another alpha emission. And then it's this kind of overall process. So you can see that overall, you have all of these transitions that have to happen. If you start with uranium-238, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 total changes, total decay processes that have to happen until you reach something that is stable. That's just going to take a lot of time because uranium-238 is so big and these decay processes are really small. So this is kind of an extreme level of number of steps, but it's not uncommon for an atom to have to undergo 5, 6, 7 steps, decay processes until it becomes stable, especially when you have something that's really far off. And so you have this, even though you undergo a decay process and they've gone to more stable, each step here does produce something that is more stable than previously. It still isn't necessarily done. Okay, first video done. Looking for questions on participation 421, going to be due on Tuesday. We haven't seen any in this video, but we still got the midweek homework due Wednesday. And then also this week, we got the lab technique presentation. That's all we're doing is the on-campus times for doing the lab technique presentation. If you're not giving an on-campus presentation, you don't need to come to lab. All we're doing is the lab technique presentation. It's just slots for on-campus. If you're doing it on campus, make sure you come to that. But otherwise, you don't need to come to campus this week. If you have any questions about anything, let me know. Otherwise, let's keep on with chapter 21. See you in the next video.